This is XR Advance, Extended Reality Advance, a webinar series, and Doug Bowman is going to be our first speaker. He's graciously agreed to participate. This is a National Science Foundation funded series in an effort to explore very specifically these 8 areas of research that need to be explored further to make virtual reality, augmented reality, and extended reality what it really could be. Our speakers have been asked to choose one of the 8 areas, and Doug Bowman has chosen optimizing the human-machine interface. And if you are signing up for this as a 590, as a seminar to get credit, then we'll email you about what the 8 areas are and how to post some discussion posts about that sort of thing. Okay, Doug Bowman. The rules about the chat are, if you are participating remotely, feel free to ask questions in the chat area of the WebEx. And Grace Nashlinas and I will be moderating, and we'll pick out questions for Doug to answer afterwards. If you're here in the room, we can also work with you on that. All right, Doug, take it away.
Okay, thanks very much, Stephen. Hope that the technology works okay and that everybody will be able to hear and see me and see the slides well. But as Stephen said, I'm going to talk about human-machine interface for VR and AR. I haven't really gotten into the swing of using the term XR yet. I'm a little bit behind the times, I guess, so I still say VR and AR. So I'm talking about research challenges in 3D user interfaces for these technologies. So I wanted to share a little bit about my background. Sorry, I think I'm getting an echo or some other audio coming through. Is that just an echo of me? No, now I don't hear anything. Okay, I'm going to assume it's okay and keep going. So a little bit about my background. I've worked in 3D user interfaces for a little more than 20 years since I was a graduate student at Georgia Tech, and some of these images are from that time, and some of them are from my time at Virginia Tech since then. But really have thought about interaction techniques, user interfaces, user experience, input devices, input modalities, all these kind of related topics. How do we effectively interact with virtual content, whether that's in a 3D virtual environment or in the real world via augmented reality? And most of the work, as you can see on the slide here, has been in VR, some also with large 2D displays, and more recently some work in AR, and I'll share some of that as we go along. I don't want to talk about any of the particular images on this slide, except to say that kind of the synthesis of all of this work really resulted in this book, 3D User Interfaces Theory and Practice, that you see there in the middle. And this was a collaboration with colleagues from around the world, so I played a part in that. But this was really kind of it became the reference for the field in terms of the state of the art in our knowledge about this field from academic research. And we recently just published the second edition of this. So the first edition was in 2005, I think. The second edition just last year. And I think it still kind of represents the state of the art in 3D user interfaces. And so I want to use that as like a jumping off point for talking about the current and future research challenges in these areas. So kind of one piece of the current state of the art as represented in the book is that we have a good set of 3D interaction techniques for the so-called universal tasks in VR and AR. So these are tasks that users have to accomplish in lots of different VR and AR applications, and they include selection, manipulation, travel, and system control. And this is one of the ways that we organize the book, and that I think about the field is in thinking about techniques that are designed for these particular tasks. So as I said, there's a good set of techniques, and the techniques have been studied and evaluated and iterated on quite a bit, and they work quite well for simple interaction tasks, or when high precision is not required. So if you're in a VR game and you want to pick up an object and throw it from one hand to the other, and then place it down on a virtual table, you can do that with the set of techniques that we know about now. So I want to focus in on one of these tasks, which is selection. So selection is very basic, very fundamental. It just means picking one or more objects from a set And obviously there's kind of two metaphors from the real world that you can draw on if you're thinking about selection in a virtual environment. So one is touching or grasping, which is what I do when I want to select my drink from the desk over here. I'm going to reach out and grasp the cup with my hand and then bring it to myself. The other thing that we do in the real world, obviously, to indicate objects is to point at them with laser pointers or with our fingers or some other pointer. So that leads to some kind of obvious natural techniques for selection in 3D environments. The touching metaphor is a technique called the simple virtual hand. You see a picture from kind of the early 90s up there on the upper right of the slide, which is a simple virtual hand, which just follows the tracker held in the user's hand. And when that tracker intersects the location of a virtual object, you're able to select the object. And then on the bottom, again, an image from the mid-90s with a pointing-based metaphor, raycasting, where I've got a kind of a virtual laser pointer coming out of my hand, and I can use that to select a more distant object. So these techniques are well known and common, and they work pretty well in simple situations. But when you get to more complex cases, they may not work so well. So imagine that you have targets that are distant. Well, I said that that's what raycasting is actually intended to do. And you can select distant targets with raycasting as long as they're not too small or they're not too densely packed with other objects or they're not moving. But in all these cases, distant targets, small targets, targets in cluttered regions, moving targets, these kind of basic natural techniques can fail unless they're enhanced in some way. So these natural techniques have limitations, and they're limitations not just due to technology, but also to the human user, him or herself, and to the environment. So certainly we still have technological problems. So if you're using a tracker to touch or to point, there's tracking jitter. There's a lack of precision. There may be drift in your tracking, and there may be latency. But even if we solved all of those problems, we would still have a human hand tremor, right? So I cannot hold my hand up in space and have it completely still. And it gets worse as I get older, right? Or the more caffeine I drink. And then there are problems with the environment, distance and occlusion being two primary ones. So I want to suggest that the first research challenge in 3D user interfaces is how do we enable precise 3D interaction with imprecise input, both on the technological side and the human side, for these kind of difficult or complex tasks. So in my group, we designed a technique called double bubble, which is a name that I like quite a bit, which is a way to extend the pointing metaphor, the raycasting technique, to handle some of these harder selection cases. So we still use raycasting to provide selection at a distance, but instead of using just a ray that is rigidly attached to my hand, instead we use a dynamic volume cursor. So at the end of the ray is a sphere, and that sphere changes size depending on what part of the environment it's pointing at. So it always contains at least one object, and it's got a minimum size, so it may contain multiple objects if you have small objects or cluttered objects. So this reduces the need for precision. It also uses a progressive refinement approach. So instead of just selecting directly the object that you want, instead we provide the user, or we ask the user to perform multiple easy selections as opposed to one difficult selection. And all of these, both of these steps, the initial selection step and the secondary selection, use something called a bubble cursor, which is this dynamic volume cursor. So that's probably a little bit hard to understand with just words, so I'll try to show the video, and hopefully it comes through well enough for you to understand what's going on. I should say that I have not yet put up these videos online, but I will do that, and I'll share them with Stephen so he can share them out along with the video in case you want to download them and see them in their full glory. So let's see if I can play this. So here's an example of a cluttered environment, right? So this is a supermarket environment. In fact, this was the setting for the first 3D user interfaces contest that was held at the IEEE 3D UI symposium. So it's a lot of objects. Many of them are far away. They're all packed together on shelves, and there are very particular ones that the user is being asked to select, and those are indicated by these red arrows here. So now let me let this play. So what you're going to see is that each time the user wants to select something, he just points the bubble at the area that contains the red arrow. And then all the objects that are inside that bubble get placed into kind of a 2D menu of sorts that comes onto a 2D plane in front of the user. The objects in the menu are still kind of linked to the objects in the world. There's some highlighting, and there's a line that goes between the objects in the menu and the objects in the world. And the objects also try to maintain something of their relative positioning in the menu. And then, as I said, both of these steps use this bubble cursor. So you can see the sphere hopefully getting bigger and smaller as you point at different parts of the environment or different parts of the menu. And with the menu, it guarantees that only one object is still in the bubble. So 2 steps gives you an object selection. So is this any better than the natural techniques? Well, it turns out that it definitely is. So it definitely handles the problem of distant targets, just like raycasting does, but it doesn't require precision. It allows you to select very small targets, targets that are very close together in cluttered regions. And although I didn't show it in that video, it also would allow you to select moving targets quite well. But I don't want you to just take my word for it. Let me show some results from a study that we did. So this was a comparison in that supermarket environment of the basic raycasting technique and the double bubble technique. And for each one, you see we've got 3 different sizes of targets: large, medium, and small. On the left is a graph for time, so the speed of the technique, and on the right is a graph for errors. So what you can see for speed is that double bubble is at least as fast as raycasting, even for the large targets. So although you have to make 2 selections, that doesn't really slow you down. They're 2 very easy selections. And when you get to the small targets, it's much faster. But then the really important thing is on the right, which shows that with double bubble, you basically make no errors. You can almost have perfect accuracy in selecting your targets. Whereas with raycasting, especially when you get to the small targets, you make quite a number of errors. So almost 1 in every 4 trials is an error with raycasting. Okay, so that's an example of the type of work that could allow you to address this first research challenge, achieving precise 3D interaction. So this idea of progressive refinement is one approach to addressing that problem. But there are other approaches as well. So something else that's been tried a lot in the literature is dynamic control display gains, CD gains. So what this means is that instead of having the mapping between the user's movement of their hand or their tracker and the movement of the cursor or the virtual hand or the ray in VR, instead of having that be a fixed mapping, we have it be a dynamic mapping. So we look at things like the speed of the user's movement of their hand and then change the control display ratio in order to reflect what the user is probably trying to do. So in other words, if the user is moving quickly, then we make the cursor move quite quickly as well. But if the user is trying to move slowly and precisely, then we slow the virtual cursor down even more. And that can allow you to achieve precision as well. Another idea that I think is interesting here is this idea of what I call virtual friction. I don't know if anybody else calls it that or not, but I'll try to show this video here. If anybody has played with Google Tilt Brush, this is just a promotional video for that. It's a painting app, a 3D painting app, where you can use a handheld controller to make brush strokes, basically, with a variety of brushes. But you're doing this in thin air, right? There's no surface that you're painting on. So the problem with painting in thin air is that you don't get any feedback, any haptic feedback, because there's no surface. You're just kind of moving the device around in space, and that can cause you to be pretty imprecise. And I don't know exactly what happens here, but there's something that the designers of this application have done to make it feel as if everywhere is a virtual surface. So there's a little bit of extra latency, or as I called it again here, virtual friction, that makes the brush moving through the air feel like a brush that's actually reacting to being moved over a surface. and it feels really nice. So I don't know that there's been any academic research on this, but I think this is another approach that we should explore more in terms of precise 3D interaction. Okay, so that's the first challenge. Let's go back to the current state of the art. So just like with all the techniques that I just mentioned, double bubble included, most 3D interaction techniques that we have today are designed to optimize speed and accuracy, at least the ones that have been studied in the literature. If you talk to game designers, that's probably not the case. Some of the techniques that we have in the literature also consider other usability factors besides speed and accuracy. So a lot of them consider comfort. So for example, we know it's not a good idea to have the user hold their hands up in front of their face for long periods of time. That's going to lead to lots of fatigue. Some of them consider things like ease of use or ease of learning or user preference. So it's not the case that we've only considered speed and accuracy, but those have been the kind of the dominant usability metrics that we have looked at. So as an example of this kind of approach, which is kind of the engineering approach to 3D user interfaces, I'll show this video, which is, again, quite a bit old, but still, I think, a pretty good example of the current state of the art. This is an application that we developed for constructing simple building structures in VR. So it's a creation interface instead of just a manipulation sort of interface. So you're starting from scratch, you build up these elements in order to make fairly complex building structures, although they're regular. So in order to make this application, we had to consider lots of things, like how the user is going to navigate to different viewpoints, how they're going to be able to select different elements to create, how they're going to be able to make large regular structures, how they're going to be able to cut holes in it, et cetera, et cetera. So you can see some of the approaches here. We have this 3D selection box that we can use to select parts of the structure. We have this kind of handheld 2D interface that allows you to do menus and buttons and the sorts of things you would normally see on a 2D interface. There's this cloning technique, which you're seeing here, which allows you to kind of quickly copy and paste different parts of the building in place. And this is a quite usable interface. It's not a very pretty interface, but it's a very usable interface. And speed and accuracy of these techniques is quite good, as is comfort and other usability sorts of issues. But I want to contrast that with some examples from current VR games. So I don't know if anybody in the room or online has played a lot of VR games, but here are two that I think are pretty good. On the left is probably the most popular VR game ever so far, although it's not a very long history to draw from. But this is Beat Saber, which is like a music rhythm game in which you hit these flying objects with lightsabers that are coming out of the controller that's being held in your hand in order to score points. And it's a really fun and compelling sort of experience. It makes you feel very powerful. On the right is a game called Overwatch, which has this mode in which you can kind of control distant objects. You can use telekinesis. You can transport heavy things. You've got basically some magic spells that you can use just by moving your hands and the controllers in different ways. So again, this is a very kind of, it's an experience that makes you feel very powerful, and it just feels good, right? So the challenge that I want to draw from this is, what are the principles that underpin great holistic user experiences in 3D user interfaces? Beyond speed and accuracy and basic usability, how do we make user experience, not just the pragmatic aspects, but also the hedonic or emotional aspects? How do we do that? And are there kind of generalizable principles that we can come up with that will help us do that? So let me share a piece of research that we've been doing recently that kind of addresses this. We were interested at first, when we started this project, in how to use hand gestures alone, bare hands, for object manipulation in VR. And we wanted to do it in such a way that it felt good. And so the metaphor that we drew from was the force push from the Star Wars franchise of movies, right? So As you know, the Jedi in these movies have the ability to control the Force, and one of the things they can do is they can use the Force to move distant, large, heavy objects from a remote position. And they do it often using accompanying gestures, although it's not clear if they have to make the gestures, but there are accompanying gestures that kind of represent the movement. And what's compelling about that is that it's understandable. It's a metaphor that we can relate to, but it's still magical. And it doesn't require us to touch the object that we're manipulating. So the user's not going to expect to have any haptic feedback from the object. Instead, it's like they're kind of moving the air around them, and that force is being transferred to the object off in the distance. So rather than talk about it more, let me kind of show you the interface that we came up with. So in this interface, you have a selected object, and the selection is kind of separate from everything else. But once the object is selected, you can use your bare hand, and which is tracked by a Leap Motion controller on the head-mounted display. Use your bare hand to create forces with gestures. So you can create very small, light forces by moving your hand short distances, and you can create larger forces by moving your hand longer distances or by moving your hand faster. So we basically look at the movement of your hand and try to kind of infer how much force are you implying that you want to apply to the selected object. So you can kind of do these big gross movements and also these very fine movements, as my student is doing here, to try to get the object in exactly the right place. You may have seen that there's also a way to rotate objects. So we rotate objects by using one finger and twirling it around to apply a torque to the object as well as force with the linear gestures. Okay, so that's kind of a cool piece of work, I think, and it feels quite nice. The question is, why does it feel nice? And so to explain this, we go to the concept of coherence. So if you follow presence research, you know that Slater and his colleagues have suggested that there are two parts of presence in VR. So one is so-called place illusion, or PI, and that has to do with feeling that I'm not in the physical location that I'm in, but rather I'm in the virtual location that's being displayed. And then secondly is this idea of plausibility, or psi, which is the user's perception that the virtual world is believable, that it kind of works the way that you would expect it to, or at least it works in a consistent way. So what creates place illusion, according to Slater, is immersion. That is, all these kind of technical factors like head-mounted displays and tracking and low latency and so on that produce the illusion that you're in that place. What creates plausibility is coherence. And coherence we define as the consistency and validity of observed behaviors and rules of a virtual world. So we think the reason that force push feels good is that it's got a high level of physics coherence. So not just overall coherence, but coherence of kind of the physical rules. In other words, the degree to which the motion and force displayed by the interface conform to internally consistent physical laws that are reasonable for the presented scenario. So if we tell people this is just like the force push in the Star Wars movies, or it's a form of telekinesis, people can understand I'm making a gesture in a certain direction, and they can understand that if I move my hand quickly and far, that's going to create more force than if I move my hand a short distance and more slowly. Right? So this coherence allows people to understand the interaction, and it makes the virtual world seem more plausible. That's our hypothesis. So, of course, we ran a study to test this. And in our study, we looked at force push and also a very basic simple virtual hand technique, and then one other technique. So let me actually play the video that shows you the other two techniques that we studied. So simple virtual hand is this kind of just basic techniques, except we're doing it remotely. So an object is selected, you do a grasping action that attaches the object to your hand, and now there's a one-to-one mapping between the movement of the hand and the movement of the virtual object. There's also no collision between objects, there's no gravity, there's no physics engine whatsoever. It just moves one-to-one with your hand. The second one is what we call the physically coherent virtual hand. So this was our attempt to apply this principle of physical coherence to a kind of a grasping-oriented technique as opposed to the magical force push technique. So in physically coherent virtual hand, there is gravity, there is collision, and most importantly, the object's weight determines the CD ratio. So if you have a heavy object, then it appears to move more slowly than if you have a light object. So you get a sense of the object's weight as well as having this kind of physical interaction of the object with the world. So I hope that makes sense. On the right are some of the results that we got. This is from the game experience questionnaire that we gave people after they experienced these 3 techniques. And the game experience questionnaire asks people about 6 kind of categories of their user experience. And what I want to highlight here are 2 of them. So the attractiveness category on the left and the stimulation category on the right. So what you can see is that this physically coherent virtual hand technique has significantly better attractiveness and stimulation than the other 2 techniques. Okay, so what do we make of this? Well, physically coherent virtual hand has objectively higher level of physical coherence than the simple virtual hand technique. So if our hypothesis were true, we would expect to get this result, that for some of these more hedonic aspects of user experience, that physically coherent virtual hand would be better, and that's what we see. The question is, why is force push not also better? Because it also has a high level of physical coherence. And what we found when we interviewed people is that they did like it. They thought it was cool, they thought it was novel, they thought it was powerful, but it's not as easy to control, right? So the aspects of kind of the pragmatic aspects of just being able to control the object and place it where you want in a pretty rapid manner, they creep into these hedonic aspects as well. So if your pragmatic characteristics are not great, then it's still not going to be the interface that people find the most attractive or the most stimulating. So we're still working in this area, but we think that this idea of physics coherence is one that can help explain, it's a principle that can help explain why a VR or an AR interaction technique can provide a better feeling user experience. Here's a couple of other techniques that we've worked on along the same lines. So we came up with some other metaphors. The first one is a tennis ball. And so in this case, again, you're doing it remotely. One of your hands becomes a ball and the other hand becomes a racket. And you can kind of hit the selected object in any direction and with any force. And again, we look at the speed of the racket when it contacts the proxy ball to determine how much force to apply to the selected object. And this also feels quite good and allows you to get an idea of the mass of the object and so on. The other one that gives you a chance to even provide more force is this slingshot controller. And again, from a distance, use your 2 hands as a slingshot, and that force gets applied to the selected object. And then you can, of course, combine these things together in different ways. So still studying these to determine what their user experience characteristics are. All right, so the second challenge then is, what are these principles for a good holistic 3D user experience? So I've suggested that coherence is one of those. I think there are probably many more that we can do research on. And this image here, which is also from Mel Slater's work, illustrates 2 of the other principles that I think might be in play. So one is accurate embodiment. Typically in VR, you're just a floating eye, or maybe you're a floating eye with a pair of hands, but you don't have a full body that responds accurately to your own body movements. And lots of Slater's research has shown that accurate embodiment can improve the sense of presence and improve the user experience. And then the other thing that this same piece of work shows is that maybe creating an emotional connection with virtual characters will improve your holistic 3D user experience. Many of our 3D user interfaces now are kind of solitary, or if there are virtual characters, they're pretty dumb and they don't respond to you in the right ways. And it's hard to really make a connection that makes you feel co-present with them. So I think more research in these directions could also address this challenge. Okay, let's go on to the third one. So in the current state of the art, most of the time we use 3D user interfaces in very controlled settings. So we have special purpose tracking areas in our labs or other facilities. We're almost always doing this sort of interaction indoors, and certainly we have to do it within range of different sensors. So as an example of that, think about placing annotations in augmented reality. So when you're using the HoloLens or another AR device, that device is trying to map the environment, right? So you see on the left this kind of spatial mapping that the HoloLens creates. It's trying to kind of mesh the environment, and from that it can determine locations that might be suitable for annotations. So a place that's sittable, or a platform on which objects can be placed. Horizontal and vertical planes it looks for. And that allows you to have experiences like this Minecraft one on the right, right? But what if you want to do this outdoors? What if you want to do this in a very large-scale environment? Well, the HoloLens sensors can't handle that, right? So first of all, it doesn't work well outdoors at all, especially in bright sunlight, and you can't see the annotations or the augmentations anyway. But also, this depth mapping sensors that do this spatial mapping don't work at a distance more than a few meters, right? So how might you solve this? How might you be able to find locations in the real world to place annotations at a distance? Well, a pretty obvious thing to do is to allow the user to tell you where objects are in the real world environment. So if you want to place an annotation at the top of this lamppost, then one way you can do it is you can have the user kind of sight at the lamppost from one location, and then sight at the lamppost from a second location, and you do triangulation and intersect those rays and figure out where the tip of the lamppost is in your coordinate system. The problem with this geometric triangulation is that it lacks precision. Again, due to head tremor, just like we saw with the hand tremor for selection, head tremor doesn't allow you to sight accurately when you're doing it at a distance, especially when the baseline is short relative to the annotation distance. So this is an illustration of the third research challenge that I wanted to bring up, which is how can we design 3D UIs that overcome technological limitations? So in this case, we're trying to use interaction to overcome the limitations of the depth sensors, but this interaction is not effective enough. So we've come up with several techniques that we use with the HoloLens to do this sort of point marking at a distance. So let me try and play this video to explain those. So the first technique is called vector cloud. It's basically a multi-sample technique. And you can see the head tremor there with the crosshair. But what you can do is you can take a whole bunch of samples from different points, or even as you're continuously moving around the space, where you're trying to look at the target all the time. But you don't have to be super precise because you've got a lot of samples and you can make an estimate of the location of the target by using all of the samples instead of just 2 rays. So here's a study that we did in VR, actually, just to avoid any issues with tracking imprecision, where we compared this vector cloud technique to the basic geometric technique in a virtual environment. And as you can see, we really like to mark lampposts. That's our go-to task. And what you see here is that both techniques had high accuracy, but the vector cloud technique had much better precision. It reduced variance quite a bit. Another way we do this is with a technique called image refinement. And with image refinement, what you do is you don't have to hold your head still at all. Instead, you just look in the region of the target, and then you take a picture. And that picture is then displayed on the head-mounted display, and you move a cursor to indicate the exact location of the target in the image. If you do that from multiple locations, again, then you can intersect those rays and figure out an estimate of where the target is. And if you have a good camera that can zoom in quite a bit, as in this simulation, then you can do a very, very accurate job with this image refinement technique. And so again, we ran the study and compared vector cloud with image refinement, and we used image refinement both with and without a zoom lens to see how that affected things. And what we found was that both having the image refinement technique, that concept, as well as having zoom, improved precision when you had marking at a great distance. Okay, so I think I'll skip past that now. So this third challenge then is overcoming technological limitations in 3D UIs, and this is just one example of a way you can do that. We're doing this interaction for point marking to make up for missing information from the technology. You can also think of redirected walking research as an example of this, right? So the limitation there is that we can't track huge open spaces yet for VR. And so redirected walking are these techniques that allow you to direct the user to stay inside the tracking area even though they think they're walking in a much larger area. And then a third approach that I think fits into this category is passive haptics or pseudo haptics. Our kind of active general purpose haptic technology is just not good enough yet. There's still a long way to go before we have high quality, effective, active haptics that are accessible and affordable to everyone. So until then, pseudo haptics, which is the idea of using replacing haptic feedback with some other form of feedback that makes you think you're getting haptic feedback, or passive haptics, which is the idea of just using pre-built props for haptic feedback. Both of those are effective approaches that can help overcome these technological limitations. So this is not our work, but I really like this video of the unlimited corridor. This is some work from Japan, where they're trying to do redirected walking, combining it with passive haptics to really improve the sensation. And so what you see on the upper right is your first-person view, which is that you're walking down this long, long, straight corridor. And every so often in the corridor, there's a doorway that leads into a cross hallway. And in the real world, as you see on the left, it's this kind of circular, cylindrical wall that you can walk around. And as you walk down this corridor, you can feel the wall with your hand. And there's a gap in the middle of the cylinder so that you could walk down one of these cross corridors if you want. And then on the lower right, what you see is that as you walk, the virtual world kind of turns, right? And so it's redirecting you to keep turning even though you feel like you're walking straight. And so the combination of all of these things produces a really nice user experience that's quite believable, even though you know that this couldn't happen in the lab that you were in when you put on the head-mounted display. All right, so that's the third challenge. Last one. So I think that the current state of the art mostly has thought about 3D interaction techniques that are fully under user control. They're kind of manual interaction techniques. So there's this fixed mapping between what the user does and how the interface works. There's been a little bit of automation. So people have thought about snapping, for example. So if you're manipulating an object, then you put the object in the location, you snap it to another object. Sorry, call is coming in here. There's also things like automatic travel to a target. So you select a target that you want to go to, and the system can figure out a way to get you there. But beyond that, there hasn't been a whole lot of work on more automated or more intelligent 3D interaction techniques. So here's an example. Let's say that you want to use augmented reality to do kind of productivity work. So maybe you want to take the windows that you would normally find on your desktop computer and put them in augmented space. And you want to arrange those windows so that you can do some task. Well, that this video shows, right? So this user has like 6 windows or so, and they can look at the windows and then make the gesture and move them around and kind of arrange them in a logical format. But this user with augmented reality is not going to be standing or sitting in the same place all the time. They are going to want to walk. They're going to want to sit down. They're going to want to move to other environments and have this workspace also make sense. But we really don't want them to have to manually grab and move all of these windows to place them in the new situation. So this is where some intelligence could come in. So the fourth research challenge is how to combine 3D UI with AI. In other words, how to do intelligent 3D user interfaces. So let me just finish off the example and kind of show you some early work that we did with this. There's tons more to do, but this is some early work by my student Wallace Lajas. So here's the kind of manual arrangement that you saw before. But once the user has kind of an arrangement that they like, then they can do a number of things. They can have the windows follow their head, right? So as they turn and look in different directions, the windows can swing around and you can work in whatever direction you want. Another thing you can do is you can tell the windows to go to the nearest wall, and the system can figure out where the wall is, and then the windows can figure out how to arrange themselves on the wall so that they maintain their basic relative layout, but the user doesn't have to place each one individually. As you walk, the windows could also follow you, right? So without doing anything, the windows could look at your position and update their position in order to allow you to keep working and to keep gathering information from them as you walk. And the system can figure out what direction you're walking, and the windows could swing around to always stay in front of you as you are walking. So here's some simple behaviors, and there's probably a lot more that we haven't tried yet, but some simple kind of adaptive behaviors. In this interface, each window is basically an agent that's trying to figure out where it should be in space, depending on what the user's doing, rather than having the user control the position of each window independently. So this is the fourth challenge, I think, is intelligent 3D UIs. This adaptive layout for mobility, I think, is one small piece of that puzzle. You can also think about, there's a lot of thinking currently about AR applications that can adapt to the environment layout. So AR applications that understand, again, what are the possible surfaces that can be used in your environment, and then change the layout of the elements of the interface based on the space that you have. VR applications could do the same thing. They could understand how big your space is, what the obstacles in your space are, and then adapt what they present to the user to make use of that space most effectively. And then the last suggestion I have here is that another way of thinking about intelligent 3D UIs is to think about human-AI collaboration. So we're doing some work on immersive analytics, which is the idea of doing large-scale data analysis either in VR or AR in some sort of immersive technology, which allows you to kind of use space to lay things out and to examine them and to make sense of them. But I think this would be much more powerful if there's some intelligent algorithms on the back end that are watching what you're doing and then making suggestions to you. So for example, if it sees that you've read several articles about redirected walking, it might suggest other articles to you and bring them into the space automatically. If I take two articles and place them far away from each other in the space, then maybe the system can infer that I don't think that they're related, and it can update its own back-end models and what it suggests based on that. So really much more of a 50-50 collaboration between intelligent algorithms and humans might be a great approach for doing this sort of document analysis in an immersive space. Okay, so I've kind of flown through lots of examples, but I hope that this has at least sparked some thinking for you. So I talked about 4 3D UI research challenges: precision interaction with imprecise input, understanding how to design for all the aspects of the 3D user experience, not just speed and accuracy, overcoming technological limitations in and through 3D interaction, and then this idea of intelligent 3D UIs. Okay, so I'm going to stop there. Here's my contact info, but I'm happy to answer questions in the room or online or however we're going to do this.
So it looks like we've got about 5 minutes, and we haven't had a lot of questions online, but I'm interested in the room here.
Hi, Doug. I'm Jim Oliver.
Hi, Jim.
I get to teach at the VR AR course in the fall, and I used a lot of your work. In fact, your book was required. There's a couple of students right here who took the class. I really like the physics coherence idea of the force. Plus, my kids love the force. They love those Volkswagen commercials and all that. When you implemented that, you have to. It seems very vague as far as inferring what I want to do from a gesture like that. Did you have to probably keep coherence of what the palm is more important than the back, or how did you map these gestures into the physics itself?
Yeah, good question. So it's basically a custom designed controller that we really just iterated on until it felt right. I wish I could say that it was more scientific than that, but it really wasn't. So we had the idea actually initially of looking at the fingers as they moved and mapping the position of the fingers to the position of the object. So it actually wasn't physics at the beginning at all. And that felt really bad. It felt like the objects were really sticky and they kind of jumped along like this and so on. And so we went to the idea of force and physics, but we had to figure out what are the characteristics inherent in kind of these rich gestures that people are doing. What are the characteristics that really matter in terms of mapping those gestures to force? And what we eventually ended up with was amplitude. So when you start a gesture, how far does it go? And also the average speed across the whole gesture. And those typically tend to kind of correlate with one another. And so we have just a mapping that says the more amplitude and the more speed equals more force.
And then this was stop. I saw that.
Yeah, we had a special gesture for stop because that seemed like a useful thing that would help you to control it a little better. Yeah.
Really cool. Is that published anywhere now?
So there was an initial paper that came out in Frontiers a couple months ago, and there's some other work under review. I'd be happy to send it to you if you're interested.
Hey Doug, John Kelly here. I just wanted to pick up on the previous question about physics coherence, and I was thinking about teleporting, which is this super common locomotion interface, and it seems to lack physics coherence. And I'm wondering if you'd agree with that and what that means about presence and whether we should be having people on treadmills or using unlimited corridors, but in particular, what are your thoughts on teleporting and its physics coherence in relationship to presence?
Mm-hmm. Mm-hmm. Yeah, that's interesting. So I think you're right that for most people, teleportation would not have a high level of physics coherence. But the thing about coherence that's interesting is that it kind of depends on the context that you set out for the user. So what is this world supposed to be and how is it supposed to work? So it might be that you could concoct a story in which teleportation was coherent with everything else, right? So I'm not suggesting that we only want kind of physical behaviors that would work in the real world in our virtual experiences. I don't think that's the only way to get a good user experience. But I am suggesting that everything in the virtual world needs to kind of hang together. It needs to make sense and be consistent with the story that you're telling. So, I mean, the game designers have a much better sense of this than we academics do in terms of constructing a story, even if it's in a fantastic world, and making that whole world consistent with itself. Sure. I don't know if that really answers your question, but
I think so. Is that maybe it's more about the potential for a link that would feel like physics coherence. Maybe like, I've seen some interfaces where you can grasp and pull as though you're pulling yourself along a rope or something. Would that be higher in physics coherence potentially, or there's at least potential for a relationship to be there in that imagined environment.
Right. I mean, I certainly would agree that if you just push a button and you appear somewhere else and there's really no reason for that to happen, it's just for convenience sake, that's not going to be a very compelling user experience. And it's probably going to make people disoriented. The more you can get the user's body and motion and force involved in it, I think the more understandable it'll be.
Thank you.
Good. Well, I think that's about it on time. Thank you so much, Doug. We'll get it recorded and send out emails about where people can find it who weren't able to make it right now.
Awesome. Thanks, guys.
Thank you.